All right, so the p-n junction that we are doing, we represent it like this. P-n here, contacts here. Okay, so these are, so we are talking about silicon p-n junction with the contacts, metal semiconductor contacts here. These are metal semiconductor contacts normally. Okay, these contacts are made here. And although we draw a p-n junction like this, is, you know from your previous exposure, it's not exactly like this, right? It's not a bar like this. It's more of, please recall, that is more of, if I take a cross section, maybe, let's say if I have a, perhaps a, let's say n-type semiconductor, and we make a higher doping here, p-type here, maybe at the bottom we have, let's say n plus. This is one way of looking at it, and you have a contact here. You have a contact here, and maybe this is a vertical p-n junction, and you have a contact here. Right? So it may look more like this, a piece of n-type silicon fabricated on n plus layer here, and then what you do is you implant or diffuse p-type layer there, and then you create a p-n junction. So when we draw this diagram here, it is more of in this region here, right? If I draw a dotted line, then my p-n junction is here, right? So it is p-n, and we are not drawing here. In general, you would find when you, in order to make contacts here, metal semiconductor contacts, somewhere here I may make a region, actually here also, at the top I may make a region p plus. So when you make a heavily doped region, and then you put a metal on it, then it forms a very good contact. Okay, so you create heavy doping next to the contact. So we are not showing that here, but close to the metal there would be a heavy doping, close to the metal on the n side there would be heavy doping, n plus and p plus layer here, all right? And the p-n junction that we are talking about is again a region, a p-n junction which has thick p and n regions. Now, thick means thickness with respect to what and all that, that we'll come to later on. But these are pretty thick p and n regions. Basically, what we are saying is that the contacts are very far away. They do not influence much. Okay. All right. So that's the p-n junction that we are talking about within those dotted lines. Okay. So in order to understand this p-n junction, obviously, we would like to get the IV characteristics. We would like to obtain the IV characteristics of a p-n junction in forward bias, in reverse bias. So all of that we'll like to obtain. In addition, we'd like to obtain maybe capacitance voltage characteristics. How a p-n junction will have capacitances in them, and more than apart from IV, CV, maybe a general purpose model, which includes the current part and capacitances and everything in it, to understand how diodes behave when you switch them on or you switch them off. Okay, so all of this understanding we've seen earlier, all of those things that you want to know, they all come from basically these equations. Poisson's equation that we talked about, del square psi, del x square, remember, minus rho by epsilon, del p by del t, continuity equations. I'm not writing it down by now, you should know all these continuity equations, and the current equation, Jn and Jp, and all of those equations. Basically, you have to solve those equations in order to arrive at what you're seeking, IV characteristics and CV characteristics, and maybe a general purpose model for the p-n junction here. Now, we had discussed earlier that the journey for that begins by looking at equilibrium. Equilibrium is the simplest situation where you have not applied any voltage, there are no external inputs, and you would like to know how does a p-n junction behave. Now, if you look at equilibrium, in equilibrium, if you would like to understand, then you would like to, again, as I said, if you would like to obtain a quantitative understanding, then the quantitative understanding is obtained from these equations. These are the equations which will give you quantitative understanding. Now, if I look at equilibrium, in equilibrium, the continuity equation is trivial, in the sense all terms are zero. Del P by del T 0, currents are 0, generation is 0, recombination 0. So they don't yield anything. I mean, it's a trivial equation with all terms being 0. Similarly, del n by del t also doesn't yield anything. Everything is 0. Okay. The equation of interest, if you want to understand what is happening in equilibrium, is this equation here, Poisson's equation. That's the only non-trivial equation. Otherwise, all the equations reduce to 0. All the terms are 0, 0, 0. It's equilibrium, 0 current, no recombination, no generation, none of that. So this is the important equation, the Poisson's equation. And if you look at Poisson's equation, del square psi del x square, is basically is talking about the potential. It's talking about how the potential inside the device, potential, electric field. So you're talking about psi, you're talking about electric field. These are the quantities you're trying to find out. How does potential inside the p-n junction vary? How does once you know the potential, of course, you take the derivative. How does electric field vary? So you're trying to find these things out, potential, electric field, and you're trying to find this out in terms of maybe in terms of what is rho inside the device. Okay, so this is the main equation that one is trying to solve in order to understand p-n junction in equilibrium, because there's no current. There's no current, but there is still inside the p-n junction, there is a potential, there's an electric field, all of that which is there, that's what you're trying to understand. Now, band diagram that you draw is a way of, one could look upon, is a way of qualitatively solving this Poisson's equation. Because look at that, del square psi del x square minus rho by epsilon. Do you recall what? Do you recall what is psi? How do we express psi? Potential inside the device. Do you recall that we had discussed that psi I can write as minus EC by Q plus some constant, some reference. So psi is related to how EC goes, or you can even write this as psi equal to minus EV by Q, whichever way you would like to write. You can psi, you can write it as minus EI by Q plus some constant, different constants, maybe different constants. Psi, you can even write it as minus E naught by Q plus constant. They're all the same. They're all the same. Why? Because we know EC and EV are related together by band gap. EC and EI are related by roughly half the band gap. So these are all the same, except that the constant terms they become different. That's all. The reference becomes different. And as I said, our interest mostly is not in the absolute value of the potential, but is always the potential difference. Okay, so it doesn't matter what the reference is. So if you look at that in equilibrium, the only equation which I need to solve in order to understand what is happening in equilibrium is the Poisson's equation, right? If that's the only equation that I have to find out, Poisson's equation, which basically boils down to finding out how potential and electric field vary inside the device. And with this relationship between potential and all that, it basically ends up finding what is the band diagram. If you want to know how psi varies as a function of x, you are saying that is effectively psi as a function of x effectively implies that what you're trying to find out is how does EC vary as a function of x? It's the same thing. How does conduction band vary as a function of x? How does valence band vary as a function of x? So in a way, when you are solving Poisson's equation, what you're trying to get is the energy band diagram. Right? You're trying to get the energy band diagram. Energy band diagram is what? A plot which shows how EC varies as a function of a position, how EV varies and Fermi and all that. It shows how these things vary as a function of x here. So that's what we are trying to do. Find out the band diagram. And before quantitatively solving the band diagram, what we do is we draw qualitatively the band diagram. So in a way, when you are sketching the band diagram of any device, what you are doing in equilibrium, effectively what you are doing is maybe you are qualitatively solving the Poisson's equation. Qualitatively. You won't get quantitative answers, but qualitatively you are solving the Poisson's equation. So let me go back to the steps of how do you get a band diagram in equilibrium, because we are going to get something important from there. Energy band diagram in equilibrium. And from there, then we'll go on. So energy band diagram in equilibrium, what is the first step? Where do you start with? Quickly, we don't want to spend too much time. Where do you start with? First step in drawing energy band diagram of any device. First step. So it's a 1, 2, 3, 4, 5. There's a well-defined algorithm for finding out the energy band diagram. First, number one step. What do you do? Of course, in your this thing, some may say this is 1 and this is 2 and all that. But roughly, where do you start with? What do you draw first? Huh? First step is energy band diagram before equilibrium. Energy band diagram before equilibrium. Energy band diagram before equilibrium. In the sense, if it's a p-n junction, we imagine as a thought experiment that P exists separately, N exists separately, they're not in equilibrium with each other. And we want to draw the energy band diagram of that. So prior to equilibrium, our starting point for that is we draw an E naught. E naught. We draw an E naught, we say this is a vacuum level. It's the energy of an electron in vacuum. So that's the first step. We draw an E naught, and then what we draw is, as I said, whatever your device is made up of, it may be made up of P, N, and all that, different regions are thought of as separate sort of a device. In a way, what you do is, your complex device, you break it up. You break it up into individual parts. So you break it up into individual parts, and then you reassemble them. See, that's one way of, anything that you're trying to understand. If you're given some gadget or whatever, if you want to understand what it is, you open it up, break it up, reassemble it, all the parts. So that's what one is doing. Break up a device into its individual parts and reassemble it. So the parts that we need to reassemble are, there's a p-type and there's an n-type semiconductor. So now with E naught there, draw a p-type and an n-type. So you draw a p-type and an n-type, how? Well, let's say this is my p-type semiconductor. P-type semiconductor, so this is EC, this is EV, and how do we locate it with respect to E naught is a reference. We locate it by saying that this is located at an electron affinity away from the vacuum level. That's the definition of electron affinity. So we locate our p-type semiconductor. This is a p-type, okay? So we locate where it is there. Along with that, we know that p-type, the Fermi energy would be somewhere here, EF. Then what we do is we locate our n-type, the other part. So n-type is also located here. N-type is also located, because it's silicon, it's also located at a energy away, which is electron affinity. So EC, EV, and because it's n-type, I know the Fermi energy is somewhere going to be here. Fermi energy is going to be here. So that's the diagram that I said you need to draw first. Draw this particular diagram, energy band diagram before equilibrium. Prior to equilibrium, you draw this particular diagram. As many parts are there. If you have a more complicated device, you break it up into 3 parts or 4 parts and draw each one of them depending on how the device is made. P, N, and if, for example, we know there's a metal. We know there's a metal also, so we may want to draw a metal also somewhere here. A diagram of a metal, because it forms a contact with my semiconductor. Similarly, there's a metal here. I may draw somewhere here also. A metal also. Metal is characterized by a work function. And so if there were a metal, for example, if there were an aluminum metal, I would draw aluminum as a work function, which is, let's say, phi m is the work function of aluminum. Where is the aluminum metal located? Fermi level of the aluminum. A metal is characterized by a Fermi level, which is located a work function away from the vacuum level. Is the amount of energy, work function, all of you know, is the amount of energy needed to pull an electron out. Similarly, here is where you put the work function. So you draw all of these parts there. The next thing is, now you imagine that these are brought together. These are all these different elements that are there, they're brought together. So in our case, we are not bothering about this for a moment. We are assuming we're not considering the metal right now. So we are bringing the p and the n type. We are bringing the p and the n type. And when you bring the two together, the first thing that you note is that the Fermi energy of the n type that you see here is here, and the Fermi energy of the p type is over here. Now, one analogy for thinking about Fermi energy is like temperature. It's like temperature tells you the direction in which heat flows, right? Heat flows from higher temperature to lower temperature. Fermi energy tells you, I think in thermodynamics and all that, you guys must have read about chemical potential. 12th class and all that, maybe, chemical potential, which tells you Gibbs free energy and all that, right? So if you recall, it tells you the direction in which one species goes. In a chemical reaction, it goes from right to left or left to right and all that. Yeah, you must have read. So Fermi energy is like that. It tells you the direction in which the electrons would flow. Electrons would flow from higher Fermi energy to lower Fermi energy. It's like that. If you recall, remember there's an expression that we had calculated that Jn was n mu n dfn by dx. We had derived this particular expression. It tells you the direction in which current flows depends on the gradient of the electron quasi-Fermi level. So gradient in Fermi level decides which direction is my current going to flow here. So now if I were to put the p and the n together, you know that the electrons are going to flow like this here. Electrons are going to flow from the n to p region here. And it's the opposite about the holes here. So the holes are opposite, so the holes are going to flow like this here. Electrons are going to flow from n to p, and holes are going to flow from p to n. So there's going to be an exchange of charge. Electrons are going to the other side, holes are going to the other side, so there's an exchange of charge. And exchange of charge, which means that my system is getting charged up. You know, if electrons leave my n-type region, my n-type region is getting positively charged. If holes leave my p-type region here, my p-type semiconductor is getting negatively charged. So there's an exchange of charge, and as a result of this process, all of you know, well, when you put two bodies into contact, eventually they have the same temperature. So when you put them into contact, they have the same Fermi level. The whole process will stop when they have the same Fermi level here. So what you do is, the next step in drawing the diagram is that you see what is happening. So these exchange of charges. The next step is that you draw a diagram in equilibrium. So in equilibrium, our starting point is that Fermi energy has equalized. That becomes the starting point, okay? Energy band diagram. In equilibrium. So first thing that we draw now is I draw a big EF. Right? So EF. Oops. EF. Constant EF throughout. Same EF everywhere. Same temperature, same EF is equalized, thermal equilibrium. That's the first step. Second step is locate the interface. Let's draw a dotted line here. Let's draw the dotted line. So my P is somewhere here, and obviously to the left of this particular line, that's the interface between the two regions here, P and N. Now in this case, what we do is, we now, remember there's an exchange of charges and all that. So what we say is that the region around the interface is sort of disturbed. It has lost charge, gained charge and all of that. But far away, nothing has changed. Far away in the bulk, nothing has changed. So what you do is, you start by locating where are my bands far away from the interface. So far away from the interface, nothing has changed. So what we say is, well, if this is EF, my conduction band must be located here. Oh, sorry, valence band must be located here, and conduction band must be located here. So I'm able to locate far away where my conduction and valence band are going to be. Far away, nothing is disturbed. It's the same. The bulk, the p-type bulk is exactly the same as it is here. Okay? Do we know this distance, by the way? This energy? How much is this? Do we know this? Huh? Can we get an expression for this? That what is EF? Let me write down EF minus EV in p-type region, what is it equal to? How much is this equal to? EF minus EV in the p-type. How much is it? Do you recall that KT ln NV by NA? NV by NA. It's positive energy that I'm talking about, NV by NA. We know this. If we know the doping of my semiconductor, I know NV and this, so I know this particular part here. So I can precisely locate where my valence band lies, where my EV lies in the bulk. And therefore I know EC and everything else. Now similarly, I go far away and I locate where is in the N type, where is my, this thing is located. So we know that it's going to be located here. It's going to be located somewhere here. We know this here. This distance we know. We know that this is going to be EC here and EV here. So we know EC minus EF in N region. In N region is KT ln NC by ND. Now of course I should put here sort of an approximation, right? Because remember, these results were obtained when the doping is moderate and Fermi energy is away from conduction band or valence band by at least 3 kT and all that, okay? So these are approximate expressions. Now, you know, we don't know how EC and EV go as you approach exactly, but we know that it's going to be a continuous curve here. So what we do is we draw like something like this here. We just connect it by a continuous curve. We don't know exactly how it goes. We continue. Some continuous curve. We draw it. Because there's no way to find out the exact mathematical variation by which EC varies with X. We are drawing a qualitative diagram. Quantitatively, then we have to solve the Poisson's equation. That's what I'm trying to tell you. Quantitatively, if you want, how EC goes is the same thing as how potential goes. We have to find that out. All right. So this diagram now, what information do we get? Why do we keep on drawing this band diagram? As I said, all discussions of semiconductor devices, any new device begins with drawing a band diagram, which is like qualitatively solving the Poisson's equation. What do I get from here? When you see a band diagram like this, what do you get from here? What all can you see? Suppose right now we constructed a band diagram for a PN junction, fine. But suppose I were to give you a band diagram like this and say, well, what information can you deduce from here, from the band diagram? What do we see? Look at the variation in EC. This is all this region is N-type. If I look at EC, EC is progressively going up, 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 and then eventually goes like this. What is happening as I go close to the junction? The difference between EC and EF, what is happening? EC and EF, the separation is increasing. So what is really happening? What do I understand? The electron density is reducing. Because remember what electron density is? Keep this in mind. N equal to NC e to the power EC minus EF by KT. Right? EC minus EF KT. So as you go from here, you find electron density is reducing. And how does it reduce? Look at that. Exponentially. So what is the electron density here? Do you know the electron density here? In this region here at this point? How much is the electron density? ND, right? At this point the electron density is ND. Now as I enter this particular region here, where now EC is starting to increase, what is happening to electron density? Very quickly it will start to reduce. Exponentially it will start to reduce, right? I mean, look at this. This is exponential here. So it will start to reduce. It will start to reduce as you go in. Okay? It will start to reduce here. So electron density is becoming smaller and smaller. Right? It's becoming smaller and smaller and all that you see here. Now, what is the electron density? Do you know the electron density here? Do you know the electron density here at this point? What is the electron density? Ni square over, right, Ni square over Na. So look at, it started, just to keep in mind, maybe let's say Na is 10 to the power 17. And let's, Nd is 10 to the power 17. And let's take Na also 10 to the power 17. Right? So, electron density starts from 10 to the power 17. And what does it end up? Ni square over Na is how much then? Ni is roughly, keep in mind, is about 10 to the power 20. Leave aside that 2 and all that. 10 to the power 20. So we are talking about electron density of 10 to the power 3 here. So electron density starts from 10 to the power 17. And where does it end up? 10 to the power 3. So in this region, what is happening is 10 to the power 17 here, somewhere 10 power 16, 15, 14, 13, 12, and all that. Eventually it becomes 10 to the power 3. Just sharply reducing. Look at the order of magnitude by which it is reducing. Right? How the electron density is reducing as you go into the region here. So are you seeing that this region is depleted of electrons? This region, once you enter this particular region here, let's say, this region is depleted of electrons. As you enter this particular region, electron density is falling from 10 power 17 to 16, 15, 14, 13. Pretty much, after a while it becomes very, very small. The whole region is depleted of electrons. Depleted of electrons because electrons are 10 power 17 here. As you enter, electron density is rapidly reducing. Same thing is happening. Whatever I am saying about electrons, the same thing is true of holes also. So as I go here, the hole density is reducing. The hole density is rapidly reducing from 10 to the power 17 here, and it will end up with 10 to the power 3 here. Hole density is 10 to the power 3 here. So hole density is rapidly reducing. So from the band diagram, we are seeing what is happening to my system here. Electron density is rapidly reducing as you go towards the junction from n-type. And hole density is rapidly reducing as you go towards the junction here. Now, do you realize that this region that you see here has charges in it, has rho? It will have charge in it. It's all charged up. Do we understand why? Why is this region charged up? I'm saying, take this region here, any point here. Why are there charges here? Why is there a charge in this region? All this region that I'm saying is all charged up. Why? So electron density is small, you agree? If I take a point like this, somewhere, let's say the electron density is 10 to the power 13, right? As you go inside, it's 10 to the power 13. At this particular point in n-type semiconductor, what else do I have? Donors, they are there. And how much is the donor density? 10 power 17. So what is rho at this particular point? Rho will be equal to Q, Nd. Note that it's always Nd minus N. If you want, you can add plus P and minus Na. At any particular point, it is this. I don't have any Na here. I don't have any Na. And hole density is also negligible. Electron density is also negligible. So what is rho at that particular point? Are you seeing that there is a charge there? Because electrons are negligible. This is negligible N. N has become small. Holes are negligible. Hole density, look, is starting from here, and hole density is becoming smaller and smaller. Hole density is small. Electron density is small. There are no acceptor atoms. So what do I end up with? A positive charge equal to Q times Nd. So this region has a positive charge. Similarly, what do you think is the charge here? Well, you should be able to show that the charge here will be equal to Qna. If you write down rho equal to Q, again the same expression. In this region, again there are very few holes, very few electrons, no donor atoms. So there's a negative charge there. So what you're finding is that I have a region which is all charged up here. All positive charges here. And all negative charges here. All negative charges are here in this region. A positive charge region and a negative charge region. And makes sense or not? If you have a positive charge region on one side and negative charge region on one side, what is the direction of the field? Direction of the field is like this, right? Does it make sense from the band diagram? Remember what is psi? Psi is what? Look at this psi here. Psi, I've been saying, is minus EC by Q plus some constant. So what is electric field? Minus del psi by del x will give us 1 over Q del EC by del x. The slope of the conduction band, gives you what? Electric field. So note the slope is negative. Slope of the conduction band is negative. It tells us electric field is in that minus x direction here. So always keep in mind here, what is the slope of the electric field? The slope of the conduction band, 0. There's no electric field. Those are neutral regions. So when you look at a band diagram, look at the slope, del EC by del x, and the slope will tell you the direction of the field. Okay, so that's other thing that we get here. So these are some qualitative things that we get. There's one quantitative information that I get from here, which is that I see that there is if you look at, I've totally messed up the diagram with lots of things here. Or maybe here. Okay. So if you look at EC here and EC here, EC on the P side and EC on the N side, far away from, by the way, so there's a region which is all charged up, and does it make sense that if I call it space charge region? Makes sense to call it SCR, a space charge region? It's a region in space where there is charge. Oh, I mean, what can be simpler than that? That name, you're calling it space charge region. All right. So we know that when you bring P and N regions together, as part of the equilibrium process, electrons and holes are being exchanged, and the region close to the junction gets charged up, and a space charge region forms. Another name that we form, which you would also realize makes sense, that we call it depletion region. We call this a depletion region. Makes sense? Because if I look at this region here, we know that the electron density is much smaller than Nd. The hole density is much smaller than Na. So this region has few electrons and holes. So this region is also depleted of electrons and holes. I mean, depleted in the sense that N is not equal to Nd. In the rest of the N-type semiconductor, I have N equal to Nd. But as I look at this region here, N is much smaller than Nd. It's depleted of electrons. And if I look at this region itself, it has very few holes also. It has few electrons and few holes. Right? So it's depleted of carriers. Depleted in the sense the carrier density here is much smaller than the doping. N and P are much smaller than doping. N and P here are much smaller than doping. So that's why we call this depletion region. Okay, it's depleted. Please remember, carrier density is not 0. It's depleted. We know that it starts from 10 to the power 17 here and goes to 10 to the power 3 here. Is getting depleted here. As I said, let's come back here and see this region here. EC here is higher than EC here. What does that mean? What does that mean? Look at this here. What is, when you think of EC, what should you think of? Minus of EC is potential. So what do you see? If EC at one side and EC at the other side. So you're seeing that the two regions are at two different potential. Which side is at a higher potential? Which side is at the N side? The N side is at a higher potential as compared to P. Note that psi equal to minus EC by Q. If EC is higher on P side as compared to the N side, it means potential is higher on the N side as compared to the P side. That's what, if you accept this, then that's what it means. P side is at a higher potential compared to the N side. Now, where does this potential come from? We didn't apply anything. Equilibrium means zero voltage. Where did this potential come from? It came about because of exchange of charges. Electrons float from one region to the other, holes float from other region to the other. There's exchange of charges, and as a result of this, you set up an electric field, and when you have an electric field, you have a potential. So we call this, as the name indicates, is that an appropriate word? Built-in potential? Built-in. So there is a potential it's not come about because of anything that I've applied. It's sort of built into the semiconductor, built into the p-n junction. It's a part and parcel of the p-n junction, built into it. So it's a built-in potential. It's a built-in potential. There is a potential difference between the p-n and the n region here. Now, as I said, one very interesting thing that we can find out is, what is the magnitude of this built-in potential? Can you see that I can find that out? Magnitude of the built-in potential. I can find out the magnitude of the okay, we need a new diagram. Okay, we need a new diagram here. All right, so let's draw the diagram here. Again, so we started from here, and we started EC from here, and EC was here, so we went like this. All right, so we had a band diagram like this. We can determine the built-in potential. Remember what the built-in potential is now? This, if I draw a line here, and we draw a line here, this is equal to what we call as Q times VBI. So this is potential, and how do you convert potential into energy? You multiply it by Q. Then it becomes EV. Okay, so that's Q VBI. So now I can determine this potential. How much was it? Very interesting. Something happened inside a p-n junction, and exchange of charges, electric field, and there is a potential inside it, a built-in potential, and I can find that out. So a general procedure for finding built-in potential is as follows. We do KVL, Kirchhoff's voltage law. All right. Remember, KVL is what? You go from one end to the other end, and sum of potentials are zero. And KVL is what? We are saying, remember, psi is minus EC by Q. Psi and potential are related together. So what do? We start from, let's say, a point. Let's go back to our red here. So we start, let's say, from okay, so from here. We start from this particular point. So I'm going to start from a point and go in a loop and come back to the same point. Okay? And I will add up the energy increments. So KVL is also nothing but conservation of energy. Okay. So what I'm going to do is, I'm going to start from point A, and I'm going to go to point B. Go here, point B. Okay? How much is that energy increment? Do I know that? EC minus? So it is EC minus EF in the P region, right? In the P region. EC minus EF. Can I also write it down? Okay, so fine, EC minus EF. We go here. Then you come down to here, point C. What happened? What is the, you see here, when you went from A to B, you gained an energy, EC minus EF in the P region. Then when you go from B to C, you lost energy. How much? Minus QVBI. QVBI. You lost energy. Then you come back to this region, D. Again, you lost how much? EC minus EF in the N region. And are you back at the same energy? You started from A, B, C, D, and D is nothing but A. At the same energy, if you want, you can come back to A. It's the same thing, loss. So the sum must be equal to 0. Okay? So all you do is, whenever you need to find potential, you need to go in a loop like this, add up energy, subtract energies, and you get difference is 0. So what we end up getting is QVBI is EC minus EF in P minus EC minus EF in N time. Okay? We are looking for QVBI. Now EC minus EF in P region, I can write it as EG, note, because in a P region, I know this Eg minus Ef minus Ev in P region minus Ec minus Ef in N region, QVBI. A very general expression for this one. Let me put it in a box. Do I know Ec minus Ef in the N region? We said we know that. Now we are making, see, this is a very general expression, no assumptions. We just, conservation of energy, no assumption. We just added up energy increments and all that. This is a perfectly general expression. Now we are going to make assumption. I'm going to write this as Ec minus Ef is Kt into Ln. We said this is equal to Nc by Nd. And we said this is equal to Kt into Ln Nv by Na. We're going to write this. Now we are making an assumption here, because this is not always true. These expressions are not always true. Okay? So you've seen that I can calculate QVBI now. Why? Because I know Na, I know Nd, I know Nc, I know Nv. I have an expression. I have an expression. I can calculate the built-in voltage of a PN junction. How much voltage is built into the PN junction here. Okay? Can we put some typical values? You can calculate, but let's put some typical values. E.g., silicon is how much? Give some typical value. Typical value what? 1.12. 1.12 here. Some value here. Let's take some 0.15. Take some 0.15. So how much do we end up with? How much do we end up with? 0.3, 0.82. 0.82. A typical value of what the built-in voltage is. Of course, you need to put in ND and NA and all that and calculate precise value. So a number to keep in mind for silicon is, I have a built-in voltage of around 0.8. It could be 0.9 also, depending on the doping. So 0.8, 0.85, 0.9. So that's the number that we get. Note that it's always less than Eg. Less than Eg. These are positive numbers. Ef minus Ev, these are all positive numbers. So built-in voltage will always be less than the energy gap. The other thing is, if tomorrow somebody gave me a different semiconductor with a band, let's say if I were to do with gallium arsenide with a band gap of 1.4, I'll get a much higher built-in voltage. If I were to build with gallium nitride with, let's say, band gap of 3 or so, I'll get a very high built-in voltage. So built-in voltage is dependent on Eg. Depends on how large the band gap is. And you will see that built-in voltage, diode currents and all that would also be related to, built-in voltage will have an impact on that. Okay. Do we know the temperature dependence of built-in voltage? So there are several things. I can get the value of built-in voltage now. I can tell that built-in voltage will increase with the band gap of the semiconductor. How will it go with temperature? What will happen as I increase temperature to the built-in voltage? Well, look, Eg is roughly constant with temperature. This Kt here, Nv, Na and Nc, Nd. Na and Nd are, let's say, all donors are ionized, so they are independent of temperature. Nc and Nv have a temperature dependence. But what is the temperature dependence, if you recall? T to the power 3 by 2. Now you are taking ln of T to the power 3 by 2. Okay, it's a weak dependence, as you can see, ln of T to the power 3 by 2. So this T is dominant. So what will happen to built-in voltage as a function of temperature? Reduce. Almost like linearly it will tend to reduce here because of this Kt here and Kt here. So built-in voltage will reduce with temperature. At room temperature it may have some value. At 50 degrees it will have some other value and all that. So built-in temperature, this thing will reduce. All right. The other thing is, please, I will leave it as a homework problem for you. show that QVBI, or let me write it like this, VBI, I've derived one expression for you. VBI is, one can also write it as KT by Q ln NA ND by NI square. Show this from the same expression except in terms of NI. This is actually a very popular expression. Most textbooks will have this expression here. VBI is KT by Q ln NA ND by NI square. Okay? So show that you can get this particular expression. All right? This expression is a source of a lot of confusion in people. When they look at this expression and you ask them what is the temperature dependence of VBI, what happens? The first thing that strikes somebody's mind is, oh, T. So VBI increases with T. That's the first answer that almost like 80% of the students give. How does VBI change with temperature? They say linearly. Increases with temperature. Why? They've forgotten about Ni square. Ni square, as you know, is NCNV e to the power minus Eg by kT. Ni increases exponentially with temperature. So that's the stronger term here. Ni increases far more than this T that you see here. And so VBI decreases with temperature. So this can be a source of confusion, but keep in mind where the temperature dependence is coming from when you look at VBI. In this expression, it's Ni square which is dominant. Ni square rapidly increases with temperature, causes VBI to reduce. All right, so now why is this so important? Because remember what we have done is, we have taken this and we have drawn this here, PN junction, okay? And what have we obtained? We have obtained, so which side is N and which side is P? So it's drawn as an NP now, right? Okay, NP junction, not as a PN junction. So what we have obtained is the difference in the potential between here and here. Agreed? Built-in voltage. As I said, it doesn't really matter what you take as a reference. So for example, I could take, this is P, I could take this, I can arbitrarily call this as psi equal to 0. Psi equal to 0. Then what is psi here? VBI. So I know the potential. Remember, to solve Poisson's equation, what was the Poisson's equation? Del square psi del x square equal to minus rho by epsilon. If I want to get the exact band diagram, I need to solve this Poisson's equation. It's a second order differential equation. I need boundary conditions. What are the boundary conditions? Psi equal to 0 here at the edge of the space charge region. Note that if you want to solve this equation, there's no point in solving it here. I already know psi is 0 or flat. There's no point in solving it here. Psi is flat. What I'm interested in is solving it in this region here, space charge region here, SCR. I'm interested in finding out how exactly does the band go. So I know the boundary condition. Psi is 0 here and psi is VBI here. I also know that at this edge here, the electric field is 0. Del psi by del x is 0. And here, of course, psi is 0. Del psi by del x is also 0 here. Electric field is also 0 here. Okay? So I know the boundary conditions now. I know the boundary conditions here. Very important that from the band diagram, I got the boundary conditions. And so now I'm ready to solve my equation here. Okay, so let's see. I'll stop after this. So PN junction is, let's say here, PNN. All of you realize that there's a region now, which is depletion region, space charge region, whatever you call. Can I now, in this region, can I draw rho? Let's call this edge of depletion or space charge region as xn, and this as minus xp. Can I draw what rho would look like? Rho would look like. Keep in mind, rho is q nd minus na plus p minus n. So if I look at this region, can you all see that it's approximately like this here? Rho equal to q and d. And in this region, there's an approximation that's being done here. What did we say in this region? Electron density is very small. Hole density is very small. There is no Na. So what is rho equal to? Q and d. So we make an approximation that rho is equal to Q ND right up to this particular and falls to 0 here. It's not going to be like this here. There's nothing that changes abruptly. So we can come back to that, and rho is minus QNA and goes like this here. So now what you have everything now, del square psi del x square equal to minus rho by epsilon. With this assumption that rho looks like this, rho looks like QND and QNA, and you have an equation, and you have the boundary conditions. You have everything available to you. You have rho also, and you have equation also, and you have boundary conditions also, so you can solve here. So what I would like you to do is, with this rho, note that this equation can be written as del E by del X is also as rho by epsilon. So what I would like you to do is, you can solve this equation mathematically, or you can solve it graphically. Why? Because note that, how do you get electric field? You have to integrate the rho. To get electric field, all you need to do is integrate, and it's a square here and square here, just integrate. And how do you get potential then? You integrate the electric field. So you can solve the whole problem graphically. Integrate it once, you get the electric field. Integrate it twice, you get the potential. And you know the boundary conditions. So go ahead and try to attempt this by yourself and see whether at the end of it, see what expression do you get of psi in terms of xn and xp and all of that. Okay? All right, so let me stop here.